Well, students, today we are going to start one very basic chapter, but it's still highly important because this makes the base of whole chemistry, and that is atomic structure. Right. See, actually, concept of atom goes long back to 17th, 18th century, and first it was proposed by Dalton that there is certain thing called as atom. Right. He called atom to be indivisible, that it cannot be divided at all. Atom itself means, actually basic meaning of atom itself is the thing which cannot be divided further. That's the meaning of atom. But later on, more researches were done, science developed, and they found that atom also consists of certain particles, which later on were called as subatomic particles. Now, one research was done by an experiment that was done by J Thompson basically, and he did one cathode experiment which we will knowing, which led to the discovery of electron. Electron was the first particle, subatomic particle, to be discovered by cathode experiment. And in this experiment, what they did, they took a tube. In this they kept a gas which was highly evacuated, not completely evacuated, because if you evacuate it completely, nothing is going to happen. So very minute amount of the gas was filled in the tube, and after that, at very high potential, discharging was done. Like this, a tube was taken. Here they kept cathode, here they kept anode, and minute amount of gas was filled up here, monoatomic gas, like this here. Now, this was connected to a very high source, and electric discharge was passed. What was observed, that from cathode, if we assume this to be cathode and this one to be anode, then a beam of electrons that was called cathode rays at that time, it passed from cathode to anode. That time scientists thought actually these are rays, they are not particles. That is why the name came cathode rays. Actually nowadays everybody knows that is not the correct name to be given for them, because they were not rays. This consisted of mass. How this was discovered? That if you put a fan here like this, which can move, small fan we put here, when these rays fall on this, the fan started moving, and when they were falling on certain thing, at that time the object became hot also, means it was transferring energy to that part. Now we will not go into that much details for cathode rays, because already in basic concepts of chemistry would have been taught to you people. So cathode rays were found later on to be electrons. Thomson, J Thompson, he got Nobel Prize for the discovery of electron. Later on, Mulliken discovered the charge on the electron, and from here it gave a new rise to a new era of models, atomic models. Now, the first one which we have to discuss, actually this is not in IIT syllabus, IIT advanced syllabus, this is only in IIT main syllabus. This was given by Thomson, which is after his name only, is known as Thomson's atomic model. And in his model, actually quite primitive, because you understand one thing, by the time Thomson gave his atomic model, even proton was not discovered, even neutron was not discovered. So based upon only electron, he gave his atomic model. One thing Thomson was sure about, that every species in this world is neutral, it is not charged. So what he said, if negative charge is existing, he already predicted, then positive mass also should exist, positive charge should also exist. Now, what happened, that he gave one primitive model which after his name only is known as watermelon model. Thomson's watermelon model, also called as plum pudding model. Plum pudding model, this one here. What he said in his model, that atom is like a watermelon. Sorry, that red pulp is nothing, it is like positive charge spread over it, and this negative charge electrons are embedded into it like black color seeds. This is what he said. Obviously very much primitive model, so did not succeed for a long time, could not explain how positive and negative are immersed into each other, but is how still atom is stable. Could not explain the spectra, could not explain the Rutherford scattering model. After some time, what happened, that at that time radioactive materials were discovered. When radioactive materials were discovered, all the scientists were doing some researches with radioactive materials, and one of them was Rutherford. he did one experiment which is known as Rutherford's alpha ray scattering experiment. For this, what he did, that he took a object and this one he filled with radioactive element. Radioactive elements basically are of two types. One will be alpha emitter, one will be beta emitter. So he took alpha emitter here, then he kept plates here to control the movement of alpha particles. He kept plates so that alpha particle will get accelerated and will move in one straight direction only. It will not divert from its pathways. Here he take like this, a disc he took. In this disc, the inner side of the disc was coated with zinc sulfide. This was coated with ZNS like this, and here he took a very thin gold foil, very thin. Gold foil, the reason for taking the gold foil mainly was because this is a noble metal and its property is that's highly malleable. So we can make very thin layers of gold. So very thin layer, single atomic layer, actually this is called single atom layer, thick layer, he took and this he kept here. Now what happened, that these alpha particles moved, went there, they hit the gold foil, right? Actually what he wanted to check, what is the penetration power of alpha particles, right? Observations which he made were like this. Zinc sulfide has got a property that when an alpha particle hits it, it makes a black spot there. Now what happened, that he found lot of black spots just at the back of the foil, lot of black spots like this. Few black spots he found here at 1 angle approximately, and very few black spots he found here, almost at these points, in this manner. Actually when Rutherford saw these black spots, he was surprised like anything when he saw these ones. How these black spots would have been made? Basically these ones would have been made if alpha particle collided with the foil here and came back. Alpha particle has got very high penetrating power, and it has got so much high penetrating power that even a steel sheet can be penetrated by alpha particle. But even a thin gold foil it could not penetrate. So that was very much surprising for gold foil, thus Rutherford here. Now what happened? This when he saw these black spots, Rutherford was surprised like anything. Why? Because he thought that all the alpha particles will penetrate through the gold foil and will pass straight through it, and we will get all the black spots only at the back, not in the front. In his own words, Rutherford, what he said, it is like you fire a 6-inch missile on a tissue paper, but it comes back and hits you. That's what Rutherford said. Now observations, these were the observations. Now results of these observations. What happened here actually, that Rutherford said that if most of the alpha particles went straight through, it means most of the part of the atom should be vacant. That is how they straight away went at the back and made black spots here at the back of the foil. Then he said, because some alpha particles have got deflected at these angles, meaning of this is that it should contain some positive charge which must be concentrated in a very small space, like this one here. This, he said, will contain all the positive charge. So when some alpha particles came nearby it, they got deflected and made black spots here, like this, from both the sides. Similarly, those alpha particles, very few actually they will be, because this volume will be negligible here. Radius of the nucleus is assumed to be of the order of 10 to power minus 15 meters. Now, those alpha particles which came straight towards the nucleus, just they were deflected back because of the very strong repulsion, and they hit it here. From here came Rutherford's atomic model. What he said, that most of the part of the atom is vacant. Total mass and total positive charge of the atom is concentrated in a very small space called a nucleus. Now to counterbalance the positive charge, the negative charge electrons revolve around the nucleus in circular pathways. This was basic Rutherford's model. Now further discoveries were done, and what was found, one law came in between actually, that is called Max Planck's, and other one was Maxwell's law. Now first we will discuss Maxwell. What Maxwell says that if a charged species is moving, it continuously emits energy. That is what Maxwell said. If a charged species is moving, it continuously emits energy. This became one of the biggest reasons for failure of Rutherford's atomic model. Why? Because Rutherford is saying that electron is moving around the nucleus in circular pathways. Now the problem is that electron is charged, and if electron is charged, then according to Maxwell law, which was universally accepted, electron must lose energy. If electron loses energy, because of the attractive forces of the nucleus, it will keep on coming closer toward the nucleus, and finally it will fall into the nucleus. Electron proton meet, that will be destruction of the atom. So atom should get destroyed in few minutes or few hours or few days only, should not last ever. Now Maxwell said this one, so based upon this, Rutherford's atomic model became obsolete, means we cannot say this is correct here. Another scientist, Max Planck, what he said, that energy is not emitted or absorbed continuously. How it is absorbed or emitted? It is emitted or absorbed in form of photons, in a packet of energy. Each packet of energy consists of certain amount of energiness, and he said this can be given by E equal to hc by lambda, where lambda is the wavelength of that particular radiation, h here is Planck's constant, c is the speed of light. Now value of h will be 6.6 into 10 to power minus 34 in MKS system. Value of c will be 3 into 10 to power 8, again MKS system, meter per second. Now the questions can be asked upon this, that we have got a radiation of wavelength 3000 angstrom. Suppose we have got a certain radiations of wavelength 3000 angstrom. The question becomes calculate energy of one photon or n photons of that particular radiation. We use the formula E equal to hc by lambda. Here the value of h will be 6.6 into 10 to power minus 34. C will be 3 into 10 to power 8 meter per second, and lambda will be 3000. It is in angstroms, so we convert it into meters. For that we multiply this with 10 to power minus 10. If we solve this from here, the answer comes in joules. So this is how the answer comes. From here we can calculate. Now on Planck's model, actually lot of problems can be created in mains also, in IIT also. So in later chapters we will discuss that in detail. Now here what happened when this Bohr's model, next one is Bohr's model, Niels Bohr.